Welcome to This Explainer. Today, we're going to demystify a massive cornerstone of organic chemistry. But, we aren't just looking at some boring static chemical equation here. We are tracking a full-on story. We're going to follow the fascinating birth, the incredibly chaotic life, and the ultimate inevitable death of a highly reactive chemical protagonist, the free radical. Now, to understand why this story even starts, we kind of have to look at the setting. Alkanes, think methane or ethane, they are notoriously unreactive. I mean, they're perfectly happy just as they are. All their electron octets are completely satisfied, their bonds are nice and tight. So how do you force an unreactive molecule to actually transform? Well, you definitely can't just ask nicely. Getting them to change their structure requires extreme conditions, like intense blasting heat or the pure energy of ultraviolet light. So here's our roadmap for today's explainer. First, the rules of cleavage. Second, we'll meet the free radical. Then, Act 1, initiation, Act 2, propagation, Act 3, termination, and finally, controlling chaos. All right, starting with Section 1, the rules of cleavage. Basically, breaking bonds. Before we actually watch our chemicals react, we have to establish the physical rules of how their bonds break in the first place. As you probably know, every single covalent bond consists of two shared electrons. And when a bond breaks, well, those electrons have to go somewhere, right? This brilliantly illustrates the two ways that can happen. On the left, we've got heterolysis. This is where one atom greedily takes both electrons. You can spot this by the standard curved arrow with two barbs. But looking on the right, we have homolysis. This is a perfectly even split. Each atom takes exactly one electron. And to show this specific move, we use a special arrow with just one barb, often called a fishhook arrow. Keep that fishhook in mind, it's absolutely crucial. Moving on to Section 2, meet the free radical, our reactive protagonist. That specific homolytic split we just talked about, the one using the fishhook arrow, that is exactly what brings our main character into existence. Let's meet the radical, or free radical. By definition, it's a species containing an atom with an unpaired electron. So the really crucial point here is that this unpaired electron makes the radical incredibly, almost desperately electron hungry. It's got an incomplete octet, and it does not want to be alone. This sets the perfect stage for total chemical chaos, because it will violently try to steal an electron from literally anything nearby just to complete its pair. Because of that intense reactivity, our radical's life cycle will always occur in these three distinct, totally predictable phases. It's honestly like a perfect three-act play. You've got a dramatic birth in phase 1, a repeating, wildly chaotic middle in phase 2, and then a definitive sudden end in phase 3. Which brings us to Section 3, Act 1, initiation, or the first break. Let's start the show with the step where all that extreme energy we mentioned forces the very first bond cleavage. This first step is simple, but man, is it powerful. When we introduce heat or light to a molecule of chlorine gas, that energy homolytically snaps the paired chlorine bond. Just look at those two fishhook arrows cleanly separating the bond, instantly birthing two highly reactive chlorine radicals. The spark has officially been lit. Next up is Section 4, Act 2, propagation, the chain reaction. Immediately upon birth, our newly minted radical acts out, entering its chaotic, fast-paced, and honestly pretty destructive life phase. Now, this is where the magic really happens. Notice the rapid-fire chain reaction here. First, our incredibly aggressive chlorine radical bumps into a perfectly stable methane molecule. It's so starving for an electron that it just rips a hydrogen atom right off the methane. This creates hydrochloric acid, sure, but way more importantly, it leaves behind a brand new radical, a methyl radical. And guess what? This methyl radical is just as unhappy. So it immediately goes and attacks another totally unreacted chlorine molecule, stealing a chlorine atom to finally stabilize itself into chloromethane. But wait, that theft leaves behind yet another chlorine radical. We are quite literally right back where we started. This cycle repeats over and over, thousands of times. The radical propagates itself, creating this massive, unstoppable chain reaction. All right, moving into Section 5, Act 3, termination, the final collision. Eventually, all that frantic, propagating energy has to burn out. The reaction can't just go on forever, right? As the reaction chugs along, the amount of starting material naturally drops, and suddenly the whole chemical soup is just filled with these roaming radicals. The life cycle decisively ends when any two radicals accidentally collide with each other. Look at the three possibilities we have here. Two chlorine radicals could hit each other, Two methyl radicals could find each other, or a methyl and a chlorine radical could meet. When they do collide, those desperate unpaired electrons finally pair up, forming a stable covalent bond. The octets are satisfied, the radical is dead, and the chain reaction completely stops in its tracks. Now, you might be thinking, is this just a one-off trick for methane and chlorine? Absolutely not. Whether it's chlorine or the monobromination of ethane that we see here, the exact same 3-act structure fundamentally rules the reaction. You see the initiation, creating those bromine radicals at the top. You see the propagation steps in the middle, where the ethyl radical is formed and then reacts to create the product. And then you see the termination steps down at the bottom. The actors change for sure, but the script remains exactly the same. Finally, let's look at section 6, controlling chaos, manipulating the mix. You're probably wondering, if these radicals are so incredibly aggressive and they just bump into things completely randomly, wouldn't that create a terribly messy mixture of products? Well, the answer is yes, unless, of course, we step in to manipulate the environment. So how do we actually get the exact product we want without the radical just tearing apart the products it just made? We do it by playing a clever game of chemical probability. By simply flooding the reaction with excess alkane, that's our starting material, we mathematically force our chemical protagonist's hand. Think about it. If there is 1,000,000 times more raw alkane in the flask than there is of the newly formed alkyl halide product, the roaming halogen radical is statistically guaranteed to hit the starting material. This beautifully harnesses the chaos. It maximizes our single substitution product and prevents all those unwanted dihalogenated compounds from forming. Basically, we are using math to completely control the madness. We've just watched the complete life cycle of a free radical in a controlled lab setting, and we've seen firsthand just how violently efficient it really is. But it leaves you with a pretty profound thought to walk away with. If a single photon of light can initiate a chemical chain reaction that repeats literally thousands of times in a flask, what else in the biological and chemical world around us relies on the sheer chaos of free radicals? It's wild to think about. Thank you so much for joining me on this explainer, and hey, always keep questioning the chemistry around you.